created an automation studio equivalent of both the power schematic and the control schematic for a dual drive conveyor belt system which we had been working on. So now before we proceed, we may want to link some images to the document so that when we do talk about things like the thermistor device or the trip switches or the thruster brake, we do know what it is we're talking about. So what we're going to do is we're just going to create linkages. Okay, so the first thing we want to link is a video file for the trip limit switches, okay, or rather just the power switches. So this device is going to be like this one. So the interest is when you click over the component on the schematic, you're able to have an impression of what that trip limit switch is, which in effect is just a pull wire operated switch. So what happens with this device is that you get to pull on the wires on either side of this, and the contacts within this unit are going to be either normally open or normally closed, which in our case would have to use a normally closed contact within this unit. Okay, and then of course the other thing we may want to link to is the thruster brake. Okay, we did mention that we're talking about the thruster brake. So the thruster brake linking would also be in the form of a video file. Okay, so we're going to link to the power contactor for just one of the thruster brakes. In this particular instance, we're going to link to thruster brake number 1. Okay, so this video file is going to be in this form, right? So the thruster brake, to just have an idea, is going to be in this form. Okay, so this is actually what we meant when we were talking about the thruster brake. So you do notice that this, think of this as the drive we're trying to control. In this case, think of this as motor number 1, right? This being motor number 1, and seeing as how this is a dual drive, motor number 2 is going to be having the same exact configuration. Okay, now on this end, right, on this end where you see something like a spring actuated system coupled to a motor, is actually a thruster brake. Okay, this right here is actually a thruster brake. You can see the thruster brake actuating. Okay, this right here, this arrangement here, is what we're targeting as the thruster brake. So the thruster brake also has a motor of its own, right? So that's what we mean when we're talking about thruster brakes. And a dual drive motor number 1 or dual drive motor number 2, this would be the motor. And then we're talking about the thruster brake 1 or thruster brake 2, we're in effect just talking about this arrangement right here. Okay, that's what we're talking about. We're talking about this motor here for a thruster brake control. Okay, and then the other thing we may want to look at is that of the TR1 and TR2. Okay, we did mention about TR1 and TR2, and we're so into talking about it being a device that was monitoring the temperature. So to put an image to that description, we're also going to link that component in the form of an image file. Okay, so we're going to link an image file to this component. Okay, and then of course let's browse for that picture, and that picture is in the form of this component right here. Okay, so what you notice is that particular component is this one here. Okay, let me just do that once again. TR1 and TR2 will be in this form. Okay, let's maybe increase it a little bit, just a tad little bit. So this will be, this right here will be TR1 and TR2. And when we talk about the coil, okay, the coil, the coil, according to this schematic or according to this image, you'd notice that based on this description that the coil is actually across A1 and A2, right? So wherever you find A1 and A2, that's the coil for the device responsible for monitoring what the motor 1 or motor 2 temperature is, right? Now, based on this schematic on the device, you notice that terminal 11 on this device is common to terminal 12 and terminal 14. And the nature of the relationship between them is such that terminal 11 and terminal 12 have a normally closed contact, whilst between terminal 11 and terminal 14 have a normally open contact. Okay. Now, based on these configurations, you decide which to use in your control circuit, okay, as it was used in ours. So that's just the thing about these components. Okay, one is for motor 1 and the other one is for motor 2 of the main drive. Okay, in this particular case, the temperature detectors have not been connected because those are supposed to be connected at points P1/T1 and P2/T2. This is why you connect your sensor 2, right? So that's just about TR1 and TR2. Now, the other point of interest that's going to be of help to us is knowing the behavior of these timers before we actually set the exact preset values for the delayed operation of these timers, right? Such as T1, T5, T3, and I believe there's another timer somewhere. So the other timer being like right here, right on top, okay? Right about here, which is T4. Okay, so T1, T2, T3, T4, and T5. Before we set the exact times, we need to appreciate the behavior of the timers, right? So to do that, we need to get into simulation, just normal simulation. Okay. Again, the only core focus is in seeing the behavior of these timers, and seeing as how timer T1 is the first operational timer, we're just going to focus on this particular one. And we're going to time it to see how the actual time stacks up against what we actually set in these timers, because normally you'd find that there's kind of a discrepancy, like you get a higher time actuation. If you set 10 seconds, you may get something in excess of 10 seconds. So we will just want to know what this 10 seconds comes out to be, right? So we're just going to time this. So to do that, we just simply need to actuate either the local start or the remote start, because R1 is going to be energized and it's the one which actually controls timer 1, right? So let's just close this point and start our timer like so, and then we'll wait for the actuation of timer T1, right? We just need to wait. We don't need to do anything but just wait and see what happens. And then, just as a point of interest, at the point where T1 is energized, we expect the pre-start warning alarms to be deactivated, right? So we're going to do this, and let's see what this comes out to be. So let's see, let's wait. And then at the point where we get this to be actuated, that's the point where we stop our timer. Okay, that's taking long. Right about there, which is almost a minute, okay? Which is almost a minute as the actual point that we get for this, okay? So now that proves to be quite an interesting outcome. So essentially what we're saying is that each second is worth about 6 seconds. Okay, so now that we know how the timers behave relative to actual time, what we're going to do is we're going to scale each of the preset values for our timers. Okay, timers like T1, T5, T3, and of course T4 and T2, right? T4 and T2. We're going to have to scale the time values. So to help us do this, we're going to have to look at the startup sequence. So first off, you notice that according to this conveyor starting sequence, it's saying that when you press the start push button, R1 is supposed to energize. So essentially what this whole thing is about, R1 is this relay coil here. Okay, this is R1. So when you press the start push button, R1 is going to be energized. That's of course assuming that the preceding contacts are all healthy, then R1 is going to be energized. So when R1 is energized, they are saying that 60 seconds later, T1 is supposed to pick up. So effectively, what that means is at the point where R1 is being energized, the pre-start warning alarms, okay, what is being referred to in here as a klaxon, is actually a branded pre-start warning alarm. So these two alarms are going to be active for a duration of 60 seconds up until the point where T5 picks up, or rather T1 picks up. So at the point where T1 picks up, at the end of that 60 seconds, or rather it's going to be like so. Okay, so R1 energizes, closes here, the pre-start warning alarms are active, and then at the point where R1 is energized, the timer T1 is active. Okay, so the way this is going to work is such that T1 is only supposed to pick up after 60 seconds. Okay, so T1 only picks up after 60 seconds. So what's going to happen is we need to set T1 to a time value of 60 seconds. Okay, so to do that, we know that we're claiming that each second of actual time is actually equivalent to, if you set a value of 1 second in Automation Studio, the actual time value is going to be like 5.5 seconds. Okay, so we're going to get the 60 seconds as required as a set value for T1, divide this by 5.5. Okay, and then that's 10 seconds with some like 900 milliseconds. Okay, so we're going to come here. I've already changed it. We're going to change it from here. So we put 10 seconds, 900 milliseconds as a time value for T1. Okay, so while here we've actually done this bit. Okay, we've done this bit. So to help us also, we may also want to do this. Okay, to help us remember what it is we're doing, we may also want to do this. We may say expected set value is equal to 60 seconds. Okay, that's what we're expecting out of this set value, that we need to actually reach a set value of 60 seconds. Now at the point where T1 picks up at the end of that 60 seconds, then T5, or rather the klaxon, is going to be de-energized. And the reason why that is because in the ladder for the klaxon, meaning this one here, we've used a normally close contact associated with the timer T1, right? So when T1 is energized, the normally close contact is going to open and the pre-start warning alarms are going to be deactivated. And of course, what we're also saying is the fact that T5 is only supposed to pick up after 5 seconds, right? So T5 only picks up after 5 seconds. So what we need is to actually just say 5 seconds divide this by 5.5. Okay, so that's like 900 milliseconds. So for T5 to be able to pick up after 5 seconds, we need to just only set this to like 900 milliseconds. Okay, we need this set to 900 milliseconds. Okay, like so. So we've actually set 900 milliseconds for T5, and the expected outcome of this is that we should be able to like get come on, we should be able to get 5 seconds out of this out of this setting, right? The actual expected actuation point is actually 5 seconds, in as much as we have set 900 milliseconds. Okay, or because of the reasons we earlier on observed. Okay, so T3, right? Now let's talk about T3. Essentially the same reasoning applies, in the sense that you'd notice that from the conveyor starting sequence that T3 is only supposed to pick up 30 seconds after T5. All right, so this here 30 seconds will need to be scaled in the same manner we've been explaining, which is to say we need to get the 30 seconds, then scale it by 5.5. okay, so this gives us like 5 seconds 454 milliseconds, right? So we come here and then we're going to say for T3, this one right here, okay, we're going to have a preset value of 5 seconds and then 454 milliseconds, right? Accept the changes and we move on. Okay, let's close this. So T3 has been taken care of. Of course, we just need to make a note of the fact that the expected time value is actually 30 seconds. Okay, you need an expected time value of 30 seconds. Moving forward, then right after T3, right? T3 picks up after 30 seconds. Then thereafter, it's all the way to energizing the thruster brakes. Essentially, thruster brake 1 and then thruster brake 2. But before that, you notice that 2 events actually occurred at the point where T5 had picked up, in the sense that C1 was immediately energized, and thereafter, 10 seconds later, T4 picked up, right? So we need to look at T4 and give it a preset value of 10 seconds. So where there's this T4 here, we need to give it a preset value of 10 seconds. So we need to scale the 10 second value by dividing it by 5.5. Okay, so which gives us 1 second 800 milliseconds. Okay, so we just need to come up here and just say we need a value of 1 second to couple to 800 milliseconds. Okay, 1 second 800 milliseconds, which is what we have done now. And then lastly, the only other timer which we haven't dealt with is the T2. Okay, now T2 is not included in the startup sequence, but rather it was somewhere up here. This is T2. You notice that T2 has got a range of between 0 to 20 seconds. We're not so sure of what that value was, so we just take the upper limit of 20 seconds. Scaling again, so we just need the 20 seconds divided by 5.5, giving us 3 seconds 636 milliseconds. Okay, so we need to change this value to that effect, that we need 3 seconds 636 milliseconds. Okay, 636 milliseconds, like so. Then accept the changes, and that's just about it. So I think we've pretty much taken care of every other timer, and we should be in a position to simulate the logic or the control system that we've come up with. So this is what we have. You may not be able to see clearly what everything is, but we just need to focus on the actuation of this. You're going to see this component turns into a RAID outline. Okay, so when it turns into a RAID outline, it means it's been actuated. Okay, so the only thing we may want also to do is we need to go into normal simulation, like so. Okay, looks about just right. But we also need to look at the power circuit. Okay, we need to look at the power circuit because we need to prep this for starting. Okay, so the only thing we need to do from here is we just need to close the disconnect and then of course close the individual circuit breakers. Okay, so that's the only thing we need to do, and then thereafter we need to go back to the control circuit. Okay, now the way this is going to work is like so, right? The way this is going to work is like so. What's going to happen? What's going to happen is this. For as long as you hold down the local start or remote start, the sequence is going to be initiated. But if you let go, the sequence is interrupted. Okay? So the point is, you need to hold down either the local start or remote start until the system latches through C3 and C4, and then the system is ready to start. But if you let go of the local start or remote start, then the system won't really complete the sequence. Okay, so our interest isn't just saying that the system eventually latches through C3 and C4, and that our drives, okay, and these drives are going to be energized in sequence. Like you're going to have M1, M2, the thruster brake 1, thruster brake 2 actuated or energized. Okay, so let's do this. We're going to hold down the remote start for the duration of the starting sequence. Okay, there we go. The pre-start warning alarms are active, and then we're going to hold on, like I said, until C3 and C4 latch the control, and then thereafter we can just let go, right? Okay, we're still active. We're waiting on T1 to be energized. Okay, waiting on T1. So when T1 is energized, which is what we are waiting on, then the pre-start warning alarms are deactivated. Thereafter T5 picks up, then T3, then T4, and eventually T2. Okay, that's what we're waiting on. Okay, so the preset alarms are off, T5 picks up, and then of course C1 is energized. Thereafter we're waiting on T3 and T4. Okay, so T4 is actuated. So T4 comes on way before T3. Okay, so you notice that T4 is energized before T3. Okay, so thereafter T3 needs to be energized before T2 times out. Okay, because T3 is the one which actually controls the thruster brakes. So now we're latched, so that you know that the sequence is like T1, T5, T4, T3, and then T2. Okay, T2 only comes on as a last resort to confirm that the brakes have not been lifted, which is why, if you remember, these we just created, right? We created this by using the C2 as an actuating contact. Okay, so I think that should be on the right, like so, or rather we used this one here. All right, we use this one here. So we said when C3 and C4 are energized, then the brake limit switches will be energized. Okay, this is what we did. So that's just about it. So when this sequence is done, from the point of view of the power circuit, all the drives are now active. Okay, these drives are just active. So that's basically how this circuit is going to work. All right. And the benefit of what we have done is that this gives you an idea as to how the sequence is expected to work. Okay, and the best way for you to do this is you've got the actual schematic, the printout, okay, and you've got on that schematic the preset time values. So the only tricky thing, I may say so, is that you need to align the actual observed time in Automation Studio to your expected time, which is the reason why we had to scale the time value so that we just get the expected performance. Okay, so hopefully this has really been helpful for you, and it's going to help us create the logic when we do come to doing the equivalent semantic step 7 control. It's going to help us better understand where we are coming from. Okay, so if I may suggest that you create this circuit, you just do step by step, go over every single step we did. Okay, and then of course, maybe just in conclusion, the only thing we may need to look at is the very fact that we mentioned of the multi-position selection switch, that there was a normal mode and there was the test mode. Okay, so we may also say we put the system into stop. Okay, we put the system into stop. So we stop the system, and once we do stop the system, we may want to put the multi-position selection switch into the test position. Okay, and then in this position we're able to test the individual drives. Okay, we're able to test the thruster brake 1, we're able to test the motor number 1 contactor, or rather the number 1 motor, the drive, and we're able to test the number 2 drive for the conveyor belt system. Okay, because it was a dual drive. And then we're also able to test the number 2 brake thruster. Okay, so we're able to test that as well. But again, it might be of interest to look at this in association to the indicator lamps to see if at all. Okay, so I've got R6. Okay, this can only be observed in the starting sequence, but to test the lamps again, remember we just needed to push the lamp test button. Okay, we just needed to push this right here. Okay, then all the lamps come on, showing you that all the lamps are in good condition, and if you needed to change one of the lamps which was broken, then you can do so, but that's just about it. That does it for the lamp test. And this other one, which is constantly on, is just the power supply on, because it's actually connected across the supply for the control voltage. Okay, so this is just it. So hopefully it's been helpful, and I do hope it's going to help us understand the logic that we're going to create in semantic step 7. So cheers.